The next topic we're going to look at is topic 4, bonding. Okay, and in particular for this particular lesson, ionic bonding and structure. So in terms of ionic bonding and structure, a lot of it will be going over previous stuff you've done last year, but we're looking at what positive ions are and how they are formed, what negative ions are and how they are formed. The number of electrons lost or gained is determined by the electron configuration of the atom, linking it back to stability and noble gas configuration. The ionic bond is actually due to electrostatic attraction between oppositely charged ions. Under normal conditions, ionic compounds are usually solids with solid lattice structures. And hopefully by the end of the unit, you'll be able to deduce the formula and name of ionic compounds and component ions. We're also going to, of course, include polyatomic ions in that discussion as well. And also explain the physical properties of ionic compounds, their lack of volatility, in fact, their electrical conductivity and solubility in terms of their structure. So ionic bonding. Ionic bond is an electrostatic attraction between oppositely charged ions. So here we have sodium chloride as our example. We have the sodium ion, which is positively charged, and the chloride ion, which is negatively charged, and because they are oppositely charged, they're going to be attracted to each other through this electrostatic attraction, which you probably looked at in physics. The other points around ionic bonding are that the bonds themselves are non-directional. Okay, the strength of the bond is equal in all directions, the electrostatic attraction. They conduct electricity when molten or in solution or aqueous. We'll look at why that occurs. We'll discuss it at least. High melting points and boiling points, and they are hard solids. They have low volatility, so they don't tend to vaporize, and they are brittle. Okay, which means if you've got a crystal salt here, if you apply some pressure, it's going to break here because it's going to be brittle. So in terms of formation of ions, let's first look at cations. So elements of group 1, 2, or 3, which are the metals, lose electrons during chemical reactions to become cations. Okay? Elements take on the noble gas configuration or structure. For example, sodium loses 1 valence electron to become the same electron configuration as neon, the noble gas. So if you look at the Lewis structure, which is this diagram here, in the formation of the sodium ion, we have this sodium electron, the outer electron. It loses this outer electron, so it ends up having a no partially filled shells, which gives it a certain stability. That's why the sodium ion, at least as a rule of thumb, is stable. In terms of formation of ions, the group 1 atoms form +1 ions, the group 2 +2 ions, and the group 3 +3 ions. Examples being there aluminium 3+. And in terms of anions, this is going to be the non-metal groups 5, 6, and 7. Okay, because they have 5, 6, and 7 valence electrons, they want to have a complete valence shell, so they take either 3, 2, or 1 electrons in order to gain this stability and become negative because they're gaining electrons. Okay, so the elements take on the next noble gas configuration or structure. So the example I've given here is chlorine, which has 7 valence electrons, but once it has gained that 1 electron, it becomes the electron configuration of argon and is therefore more stable. Again, looking at the Lewis structure, for this time an anion, a chloride ion, we start off with 7 here with the chlorine atom. It gains an electron, so now this extra electron completes the octet on the outside shell, so it therefore stabilizes it. So just as we did with the cations, group 5 form -3 anions because they have 3 electrons. Take 3 electrons to get that full octet. Group 6 take 2 to get the full octet, so they're -2 anions, and group 7 take on 1 to become just the fluoride, chloride, or bromide, the -1, because they just have that 1 electron they grab to get the octet. Okay, so transition metals, which we've just looked at, form more than 1 ion. They have variable oxidation states. The example I've given here is iron. It can form both iron 2 and iron 3 plus because it can either lose 2 electrons to give the stable 3d6 configuration, after losing those 4 s electrons, or 3 electrons, due to the lower energy, ionization energy differences between 3d6, 3d5, as opposed to the large jump that you would get if you took, say, 4 electrons away from aluminium. So in terms of ionic bond formation, we've already looked at this briefly on the last topic. You can use your periodic table to work out if an ionic bond forms, because they generally form between metals and non-metals, or you can use the electronegativity values also from your data booklet. Okay, so the degree of polarity, so that's the degree of where the electrons are going to go, can be determined by looking at the difference in electronegativity. So what I mean by polarity, okay, so here, classic example here is HF, okay, so you've got your 2 electrons, your 2 bonding electrons forming this single bond between the hydrogen and the fluorine. Fluorine has more protons, it's more electronegative, so essentially the electrons like to live around fluorine, so that becomes something called delta, slightly negative, and the hydrogen becomes slightly positive, okay, more acidic in a way. So it roughly breaks down like this. So if the values, difference between the elements in the bond is between 0 and 0.4 in terms of electronegativity, it's going to be a non-polar covalent bond. If it's between 0.4 and 1.8, that's a polar covalent bond. And if it's greater than 1.8, you're looking at ionic bonds. And just reinforcing what we did in the last unit around electronegativity. Electronegativity, remember, is the ability of an atom in a molecule to attract electrons to itself. So the previous slide, that was fluorine, has a very strong ability to do that due to its high atomic charge. And you can see this on the periodic charge or chart on the right. Okay, so electronegativity increases as you go up a group, which makes sense in a sense because you've got smaller and smaller electron orbital shells. Okay, getting closer, the electrons are getting closer and closer to the nucleus. Positive charge, there's more pull on the electrons, so that makes sense. And also as you go across a row, the electronegativity also increases because the proton number is increasing, and again there's more effective pull on the associated electron that's being attracted. So that's for atomic ions, or elemental ions, I guess. You can also have polyatomic ions. So common polyatomic ions form by essentially the non-metals in period 2 and 3, and you must know them, okay? Know their formula and also their charge, because we'll be using them a lot in class, okay? Very important. Okay, so in terms of describing the lattice structure, okay, here's an example of a small sodium chloride ionic lattice, okay? So we have the every sodium ion here is attached to a chlorine atom, okay? So that's a 6 to each chlorine, so it's a 6 to 6 ratio, or 1 to 1. That's why we have the formula as being sodium chloride. And you'll also notice the bond difference is equal for each of the sodium chloride ion interactions in each direction. Okay, so that means the bond strength is equal for each of those sodium chloride electrostatic interactions. So this in a way explains the high melting point, because you've got so many ionic bonds to break that requires a large amount of energy, and also describes why they're not gases, because those molecules are locked, or those ions are locked into this rigid kind of crystal lattice, so it's going to be a solid. There's a bit of vibration around those points, but they don't move freely like a gas could. Okay, and we'll now look at solubility in the next slide. So if we look at water in a conical flask, for example, this is what it would look like molecularly, okay, if we went down into the solution itself of pure water. Okay, you'd just be a whole range of water molecules floating around in three-dimensional space. But then, what would happen if we added some sodium chloride? Well, here we have the atom of sodium here, okay, the sodium ion anyway, Na plus, and a chloride ion, Cl minus. And you'll see what happens is that because of the polar nature of the water molecule, the hydrogens end up being slightly positive, okay, and the oxygen becomes slightly negative. Okay, so that's the oxygen, that's the hydrogen, and that's the hydrogen. And the water molecules orientate themselves, okay, in order to stabilize the associated charges on the ions, okay. So the sodium ion is attracted to the slightly negative oxygen atom of water, and the chloride ion is attracted to the slightly positive charge on the associated hydrogen atoms, because water being a polar molecule means that the electrons tend to move to the oxygen because it's more electronegative than hydrogen. Okay, so that's how, in a way, water solvates the sodium chloride in solution. Okay, it's no longer a lattice, it's now being broken up into sodium ions surrounded by 6 water molecules, and chloride ions being also surrounded by 6 water molecules. And if they weren't there, then they would again join up and form this 3D lattice that we are now familiar with. Okay, so the water would go in and actually break these electrostatic interactions between the sodium and chloride ions, because the bond between the electrostatic attraction between the water molecules and the chloride and sodium ions is stronger than the electrostatic interaction between that of the chloride ions and sodium ions in the lattice itself. Okay, and this is what it looks like as we come out, the actual sodium crystals. Okay, so I've just kind of zoomed in terms of crystals, and there we have the salt now on our table. So that's what actually we're looking at when we are looking at salt. We're actually looking at a crystal